Okay, welcome to chapter 8. So we are going to continue with the chapter on heteroskedasticity. We know that one of the classical linear regression assumption is that there mustn't be a problem of heteroskedasticity, which simply implies that the variance of the error term must be equally distributed, so which means it should be homoskedastic. So if it's heteroskedastic, then it is a problem because it will have an implication on the OLS estimators. Okay, so let us look at what are some of the consequences of heteroskedasticity if you are estimating using the OLS. One of the problem is that if you are using the ordinary least square to estimate a model in the presence of heteroskedasticity, then you are going to have a problem of the variance formula on in the estimators because it overstates the variation, and that's why you'll have that unequal spread in the error term. So, and remember that the error term is supposed to capture the factors that are affecting the model, but you don't want them to be captured within the model because you assume that the model that you have estimated is a true model, and so therefore we do not want that effect being reflected. So one way of dealing with that is by um, estimating the so-called robust heteroskedasticity type of model. So because we know that if we just go ahead and use this OLS by, to estimate a model, our F and T tests will actually be invalidated. In other words, they won't be useful at all. Because of the presence of heteroskedasticity, and for that reason, the OLS estimators will no longer be best linear unbiased estimator, so they won't fulfill the blue property, and so that is going to be a problem in it. Of course, they might be unbiased and consistent, but they might naturally not be as good as they are supposed to be. And so, and as I said, one way of dealing with this is we can actually estimate the so-called heteroskedasticity robust inference using, and this is basically very, it's provided in most software packages, and I'm actually going to show you in eViews how to estimate that. Um, and usually what happens is that if you estimate the um, the so-called heteroskedasticity robust type of model, then that means that when you use those formulas, then the t-test become valid asymptotically. And that means that as the sample become larger, larger, and larger, so the standard error start to move toward zero, and so you have a minor variation, and you have an equal spread amongst the within the model. And then of course it also then means that the F statistics, what usually now happens is that the, the the usual F statistics does not work under heteroskedasticity, and that's why if we have the robust heteroskedasticity version, then we can actually then we don't have to worry about the problem of heteroskedasticity. So that is just to say that instead of estimating the usual OLS with with your normal OLS standard error, we would rather use the heteroskedasticity robust when we are using the OLS, and I'm actually going to demonstrate that in eViews. All right. So here's just an example of what happens. So what you have to understand here is that usually the null hypothesis is that the model is homoskedastic, meaning that there's no problem of heteroskedasticity, while the alternative hypothesis is that there is a problem of heteroskedasticity. So usually we do not want to reject the null hypothesis, but because the null hypothesis basically say there's no problem of heteroskedasticity, and that is basically what we want. So, but what I want you to understand is that the fact that we are estimating the robust heteroskedasticity standard error does not mean that there is going to be a major variation. Sometimes you have a situation whereby these heteroskedasticity robust standard errors might be larger, sometimes they might be smaller. So they can go either ways. So, but we know that the differences are really smaller in practice. But what we know, even the F statistics are usually not far from each other. But what we know is that if there is a strong heteroscedasticity present in the model, then the differences might be larger. Okay, but if the heteroscedasticity present is really minor or meager, then the difference won't be that big. But what we always advise is that it's always rather advisable to estimate the to compute a robust standard error. Then how do we test for heteroskedasticity? There are many tests, okay, and we are just going to concentrate on a few of them, and these tests are usually provided within the software. The first one is that of the brush pattern, and again, here is just to show you manually how the equation looks like. Here you basically because remember that our null hypothesis is that the the error of the variance of the error term must not vary with the variables, or we can simply say the mu squared must not vary with the explanatory variables, so that we don't have that problem. And that is the null hypothesis. And the alternative hypothesis is that obviously they do vary. So in essence, we do not want to reject our null hypothesis. So the brush pattern is there. So what you do is you always look at the p-value. So in essence, we want our p-value to be higher than 0.05, because if they are higher than 0.05, then we cannot reject the null hypothesis. But if they are smaller than 0.05, we will actually then reject the null hypothesis. So, and that's basically what we look for. We look at the p-value when we estimate the equation, and I'm actually going to show you later in the practical video. And so here is just to show you how the equation looks like. But this is not important because we do not do these things manually. Of course, back in the days, these things were done manually, where they had to create a residual and then they had to regress that residual against all the explanatory variables so that they can get their value, and then they use the f-test to test so that they can decide whether to reject or not to reject a null hypothesis. So for now, you do not have to worry about this because the software packages actually do provide these tests. All you have to do is just a click of a button. And then another, of course, this is just an example which shows the difference between the when you have the model that is you know you see, for example, the p-value that I was telling you about. So this is a model with heteroskedasticity, and this is the model without heteroskedasticity. So in this case, they use the LM test to test for heteroskedasticity, and you can actually see that this 0.0028 is less than 0.005. So hence, they did reject the null hypothesis because the p-value is less than the level of significance, and we use 5% in this case. And in this case, we can see that 0.25 is actually greater than 0.05, and therefore we could not reject the null hypothesis of homoskedastic, or the null hypothesis of no problem of heteroskedasticity. So, and that's why this is basically what they are trying to demonstrate with these two models. And as I said, I'm going to show you how to do that in the regression model. And the other test that is usually used also is the white test. So it's actually called the general test for heteroskedasticity. So this is the white test, and then again it follows the same hypothesis, the null hypothesis, no problem of heteroskedasticity. The alternative, there is a problem of heteroskedasticity, and once you look at the p-value, you can then decide whether to reject or not to reject. And there are two versions of this white test. You have a version where you can include you regress the squared residuals vis-a-vis all the exploratory variables, their squared terms as well as their interactive terms, meaning you have included the cross terms. You have also another one where you do not have to include the cross term. So, and I'm going to show you both versions. Usually you are at the liberty of deciding whichever. The only disadvantage with this one where you include the cross term is that if you include all the squares and interaction, it leads to a large number of estimated parameters. You might end up having too many parameters to estimate for, and that in itself is not really a good thing. Though it's not a problem, but sometimes it might cause certain problems. So that's why we would rather maybe use the one that does not include cross terms. But then again, there is a debate in literature that use the one with the cross terms. So that's why I'm saying you are really at liberty at deciding which one to use. There's no consensus, so to say. Alternatively, you can use a different formulation of this equation. Here you can see you have regressed this vis-a-vis the explanatory variables. With the next version, you are regressing the residual vis-a-vis the dependent variable and the dependent variable squared. And so that is the difference. And so that is the difference. You can also use that version, but again, it follows the same hypothesis that you are testing. And that brings us to the end of this part 1 of the lecture.